Okay, so, yes. See you after class. Okay. Okay, so, how's everyone feeling today?
Totally awesome, sir.
Gary, if it's wrong, just see me after class, okay? If not, I gotta get this show on the road. Alright, so, we were talking about the fact that Newton was the first to propose that the same force that pulls down an apple pulls down on the moon. It's not the same magnitude, it's not the same size force, it's just the same type of force. It's the force of gravity. Gravity pulls down an apple, gravity is pulling in on that moon. Yes? Newton went on to say, well, the Earth can't pull on the moon without the moon pulling back on the Earth just as hard. This is the same sort of thing that happens with the sun and the Earth. The sun pulls in on the Earth with the force of gravity, but the sun can't pull in on the Earth without the Earth pulling back just as hard on the sun. Look, the force of gravity looks like a little nose. So then Newton got thinking, you know what? It's not just the Earth and the moon, or the sun and the Earth. It's any two masses. If you have any two masses in the universe, mass number one, mass number two, it could be you and your table partner right now. Any two masses in the universe, they naturally attract and pull each other. You guys are all funny. Now, when Newton proposed it, he couldn't test it out, but eventually, a gentleman by the name of Cavendish verified this, and today we know as fact that any two masses in the universe, me and this pen right here, have a force of gravity that's pulling us together. Now, of course, we don't feel it because it's small unless one of the masses is like the size of a planet. But the truth of the matter is, if I took one of you and took another of you and put you in outer space and then just let go of you, gravity would pull the two masses together. Why does this happen? No one even knows. It's just the way it is. Ladies and gentlemen, this was big news. This is what Newton discovered, that the law of gravity acts between any two masses in the universe. He went even and figured out exactly how to calculate this attracting force. He said that if you know the distance r between the two masses, between the center of one mass and the center of the other mass, and you know the mass of each object, m1 and m2, if you want to calculate this force of attraction, leave a little space right here. You take the mass of one of the objects, multiply it by the mass of the other object, and divide it by the distance between them squared. That'll end up telling you how much the two objects are going to be attracted towards each other. Now, if you take and multiply the mass times the mass and divide it by the distance squared, the answer will not come out in newtons. If you want the answer to come out into newtons, you need a proportionality constant built right into the formula. Newton never figured out what this proportionality constant was, but he knew there had to be one here, and it had to have the same value throughout the whole universe. We now know that this value is 6.6 0.67 times 10 to the negative 11th Newton times meter squared over kilograms squared. And at first those units look kind of complicated, but if you look how that's going to be substituted into the formula, and on the top of the formula you have the masses. So you have M1 in kilograms, and then you have M2 in kilograms, and then down here you have the distance between the two in meters, and that gets squared. So when you multiply the whole right-hand side out, all the units cancel out except for one. What are you left with? Newtons. So this will give you the force of attraction in newtons. But the two masses have to be in kilograms, and the distance between the two has to be in meters. This constant is known as the universal gravitation constant. So let's go back and calculate some of these forces of attraction. You ready to roll? So let's start off with this one. In our handy dandy college textbook, right, open the front cover, you have some useful physical data. It tells us that the mass of the Earth is 5.98 times 10 to the 24th kilograms. So 5.98 times 10 to the 24th kilograms. Okay. The mass of the moon is 7.35 times 10 to the 22nd kilograms. 7.35 times 10 to the 22nd kilograms. That's how much matter, how much material. The mean distance between the moon and the Earth, the average distance, is 3.85 times 10 to the 8th. So the distance from here to there, center to center, .85 times 10 to the 8th meters. Knowing those values, using Newton's universal law of gravity, we could actually calculate that gravitational force of attraction. Big G, newtons times meters squared divided by kilograms squared. That way, all the units end up canceling out except for the newtons. Now when you put this in your calculator, folks, you should definitely be using your EE button. If you want to put in the first value of 6.67 times 10 to the negative 11th, you should hit the button 6. And then the point button, and then another 6 key, and then the 7 key. But instead of hitting times 10, you should hit your Shift EE button. And then hit the negative sign, and one button, one button. That EE button, right there, that takes care of the times 10. Of course, there's other ways to put that number into your calculator, but this is the fastest, best way, because it keeps the number together as one. Otherwise, you run into trouble when you go and you square, or when you divide. Order of operations gets messed up. So what do you end up getting when you calculate that out?
1.97 times 10 to the
1.98 times 10 to the 20. You're getting 20th?
I got 25.
Did everyone square that denominator?
I did.
Which is double check that, Dylan. Did you guys get that? Dylan, did you get that now?
No, but
Now, let's bring it back to a closer level. Let's say we have two students, like you and your table partner, and you're about 1 meter apart. Let's go ahead and calculate that one. Average mass, 50 kilograms. Say you and your table partner, 1 meter apart. How much is this mysterious force of gravity that at this very moment is pulling you towards your table partner? 10 to what? -7? If we write that without scientific notation, 1, 2, 3, 4, 5, 6 zeros, right? 1, 6, 7. And remember, a Newton is 1/4 of a pound. So if you wanted to measure in pounds, you didn't have to even make it smaller, divide it by 4. So it's nearly impossible to measure this force of attraction between such small masses. However, someone actually did it. His name was Cavendish, and we'll take our 2 o'clock stretch, and then we'll talk about how he verified Newton's law. Yo.
How do you use the EE on
It was like
Second,
yeah, how
second.
am I gonna look at this?
For the times 10 would be.
Instead of doing times 10, you say 6.67. But you don't get times 10 anymore. Second, you don't do like that. And that little E symbol stands for times 10. -11. Now, Cavendish cleverly hung up wire from the ceiling. It was, fairly stiff wire, and from this wire, he connected a wooden dowel, like a wooden rod, and on each side of this rod, he attached a bowling ball. Perhaps it wasn't a bowling ball, but it was like a bowling ball type mass. They were the same size, same mass. And if you just breathed on one of the bowling balls over here, the whole apparatus would swivel on the wire. I have a chemical model here just to kind of show you. The string here would be like a stiff wire, and he balanced it just right. A few bowling balls. Oh no, I'm gonna balance. If you just sneeze, achoo, it would swivel. It didn't take much, even with the stiff wire. Now with the stiff wire, it would just move a smidge and then come on right back because the wire didn't like to be twisted. The wire twisting almost acted like a spring effect, and it would spring and then bring it right back into place, yes? And basically, he took this apparatus and
I feel like the one on the right is just much
thank you. And the apparatus, the experiment wasn't really between these two. This was just used as a mechanism to balance off this one over here. And, boy, it's delicate. Alright, it's just gonna take a moment
on physics.
here. Oh, physics. Wait. Okay. So here's what he did. He brought another bowling ball mass, yes? Alright, and this would be like stabilized, not moving. And when he brought the other one near over here, yes? Then guess what this bowling ball over here ended up doing? Moving towards it ever so slightly. It actually swiveled towards it. Oh my god. No, I'm joking. Yeah. It actually just swiveled towards it. And if you put it on the other side, it swiveled back towards the other side. And basically, he could determine how much force it would take to twist the wire, you know, like let's say 5 degrees. And by the amount that the wire got twisted, he knew how much force was being exerted on the ball. So basically, by taking another object, it's like three-dimensional here, hard to draw. By bringing it, let me try this again. I'll try back here. Another object back over here. Okay, basically, this ball here would attract towards it, and the whole apparatus would swivel. And the amount that the wire swiveled indicated the force, and he knew the mass of this object, and he knew the mass of that object, and he can measure the distance between the two, and he determined with the force by how much the wire twisted. And by doing this, he used Newton's formula and worked backwards to solve for big G. So Cavendish not only verified Newton's law, he actually found the value of big G. Now think about this, folks. When he found this value out, it immediately led to the knowing of the mass of the earth that we live on. Let me show you what I mean. Can I go on to the next slide? This here is the distance between the two objects. You know, maybe I should like that. So the Cavendish experiment verified Newton's law of gravity and determined the universal gravitational constant. When he published his paper, the title of it was something like, I found the mass of the Earth. It wasn't quite like that, but it was something like mass of the Earth discovered. So let me show you, once you know big G, you can determine the mass of the Earth. So let's go back now, or let's go to another page here. All right, don't say that. That'll be in my mind all day.
In my mind for like the past 2 days.
I know. Mars is a world of wonder. Okay. All right. Oh, here we go. Here's the Earth. And, here you are standing on the Earth. And you know your mass. You could put yourself on a double pan balance and determine your mass, 50 kilograms. You could hang yourself from a fish scale, measure how much you weigh, yes? Or you could use Fg equals m times g. So you know your weight. That's how much the whole Earth pulls you down. Newton's third law of motion says, well, the Earth can't pull you down without you pulling the whole Earth upward with the same exact force. Now, if you know the distance between the center of you and the center of the Earth, which basically boils down to what? The radius of the Earth. If you know the radius of the Earth, and you know what that force is, 500 newtons, and you know what your mass is, m2 is 50 kilograms, if you want to work the formula backwards, you could solve for m1, the mass of the Earth. Fg equals big G, m1 times m2 all over r squared, and we have values for everything except for m1. So when Cavendish discovered the universal gravitational constant G, he was immediately able to calculate the mass of the Earth. Now, does anyone know how they figured out the radius of the Earth back then, or the size of the Earth? The famous experiment that... No? No, they didn't travel the world at that point. Good. It was some sort of experiment with the sun, and basically the light rays from the sun is so far away that the light rays are essentially parallel when they hit the Earth. parallel to each other, that is, the light rays, sun. And if you put up a little pole at this particular place on Earth, and then you put up another little pole over here, yes? Well, when the light ray comes and hits, you're going to get a little shadow right there in this area right here. And up here, you get another shadow area over here. And if you had like a friend who lived, in another area, and you agreed simultaneously at noontime, put a 2-meter high stick perpendicular into the ground and measure the shadow, well, if you knew the distance between the two poles and you knew these little shadow lengths, there was a way to actually determine the circumference of the Earth, the size of the Earth. And then once you knew the circumference of the Earth, you could figure out the radius of the Earth. I'd have to refresh my memory how they figured it out from those two shadow lengths and from the distance between the two poles. Maybe you need to know the height of the poles as well. But a pretty interesting, simple experiment. I've known high schools that they've done the experiment where they got somebody like in North Carolina, at noontime, to measure the shadow, and up here they measured it, and then they used the calculations to figure that out. All right, I'm game. So the radius of the Earth is 6.38 times 10 to the 6 meters. So, what started off as an apple hitting Newton in the head led to a universal law that any two masses in the universe get attracted towards each other. And if you want to calculate that force of attraction, you need to know the universal gravitational constant times the mass of the first one times the mass of the second one divided by the distance between the two squared. And that's what physicists mean when they say Newton discovered the law of gravity.